Go ahead and push, just to be safe. So we just hit the record button. All right. All right, let's not take away from the people that showed up on time. Go ahead and get started, Joe.
Okay. Well, welcome to another L3 webinar for Technology Review. My name is Joe Holliday. I'm the Business Development Director for Danfoss Drives. And today we're going to discuss some harmonics reviews. This presentation I built for an engineering company in Texas who gave us an agenda of what they wanted to discuss. They specifically wanted to know some causes, what are harmonics, what's the difference between current distortion and voltage distortion, and what are the mitigation techniques that are available today. There's a lot of different ways to skin the cat, so to speak. There is no one size fits all for harmonics or harmonics mitigation. Some of the slides here are slightly repetitive. If anybody in the audience does any kind of instruction or education, you'll realize that sometimes when you tell people or show people the same material in a couple of different formats or a couple of different ways, it tends to sink in a little bit better. So feel free to interrupt with any questions that you may have. We will have time at the end to go over Q&A as well. If I don't know the answer, I will definitely make sure that I've recorded your question and get the experts on the phone. So launching in, we'll do the overview. Like we said, talk about voltage and distortion, voltage and current distortion, talk about what our mitigation solution options are, and then one of the things we'll focus a little bit heavy on is passive filter functionality. One of the things that's really, really important in today's world is energy efficiency. And I'm not a huge fan of just reading statements off slides. This is my first webinar, so it's a little bit different, not standing in front of people, but there are some details and some data points about the use of variable frequency drives in AC motors throughout the market. And as I mentioned earlier, I'm not sure if anybody heard, but there are some industrial folks here and there are some water people here as well. My focus is in water and wastewater. And what we've discovered in the water market is 80% of the electric motors that ship into the water market do not have a drive on them, meaning 20% would. You can see here 25% of the electric motors globally are controlled by a drive. So there's a huge opportunity for me as a sales guy to get some big wins, but even bigger, the opportunities for energy savings. And I'll very briefly touch on the energy savings. If you reduce the speed of an electric motor by 20%, you cut the energy required to run that motor in half. And those are the affinity laws of physics. So think about that. If I just go from 100% speed to 80% speed, which in most municipal wastewater treatment plants, they're running between 60 and 80, sometimes 90%. So you gain a huge energy savings. So keep that in mind. Now, how does that relate to harmonics? Harmonics obstruct the energy savings. There are losses in the system, and that's what we'll discuss today, and how can we resolve those losses. So before we get started, or as we get started, it's important to understand how a drive works, and I apologize if there's any redundancy here, if this is a little too basic, but the fundamental of an AC drive is we take in AC power, we convert it to DC power in a rectifier section, we store it in a DC bus, which is basically a capacitor, and then we use that energy and we pulse that energy back out to the motor with insulated gate bipolar transistors, which is IGBTs. It's an industry standard. It's nothing specific to Danfoss. And we send that energy to the motor. It goes through the coils of the motor, generates a magnetic field. Inside the motor is a rotor. It chases that magnetic field around in circles. The shaft of that rotor is connected to a pump or a fan, or in industrial applications could be a conveyor or a lift crane or something. And that's where we get our work done. The harmonics portion of that system is based on the front end, or the rectifier system. In the upper right-hand corner, you can see what's called a 6-pulse diode rectifier. There are two diodes per phase, and you can see A phase, B phase, and C phase right here, and you can see each one has its own diode. And what happens is, as energy flows, the diode is an electronic circuit that allows energy to flow in one direction only. So think of it like a check valve in a water line. So when the energy goes up through diode number 1, it gets to a certain point, the diode opens, and that positive AC power switches over into our capacitor. As it goes through number 2, it comes back the other way, and so forth. What happens, and I have an abbreviated example here, the blue line is phase A, the red line is phase B, the gray line is a DC bus voltage. I try to relate this back to water. If I have a plastic water bottle and I'm trying to fill a paper cup, and the plastic water bottle is below the paper cup, and I empty the bottle, it doesn't go into the cup, right? So if I look at the water bottle in its position as voltage, it has to be above the paper cup in order for the water to fall into the cup, right? Makes it kind of simple. So what happens here in the gray line is the DC bus voltage is here. The phase and A phase voltage comes up to here. When the A phase voltage exceeds the DC bus voltage, that's where my diode opens, and I get a certain amount of current flow, which is this light blue line. As soon as it falls back below that threshold, the diode closes, and I end up with this pulse. And you'll hear the term, and you'll see it later in the presentation, as a 6-pulse rectifier or a 6-pulse drive. And we'll go over 18-pulse drives later when we talk about mitigation solutions, but that's where the term comes from. If the third phase was on here, you would have a third light blue pulse, and you would get 6 pulses. Well, when you plot that out in a oscilloscope, you end up with a waveform that looks like this. It's clearly not a sine wave, because it's a function of all the things that we'll talk about in just a few minutes, the different frequency levels and currents that are associated with those frequencies that are in there. And this is what's referred to as a nonlinear load, because we don't draw voltage and current at the same time. Other examples of nonlinear loads are switch mode power supplies, UV lighting systems, UPS systems, variable frequency drives, arc welding systems, anything like that. So that's the basics of where this comes from. Different drives will have different harmonic waveforms. So any periodic signal, which is this green line here, can be represented as a sum of the sine waves. And we employ what's known as Fourier transform, or fast Fourier transform, Fourier analysis, if you will. And we simply look at these waves and try to break them out into what they would be. What happens because of the pulsations and the distortions, and to really simplify this, what I tell people is harmonics are simply distortions in the AC waveform that go from the drive back to the power utility or the transformer. There are other issues of noise from drives related to the motor, but that's downstream of the drive. When we talk about harmonics, we're talking about issues between the drive and the power supply itself. Because we do what's called full wave rectification, if I go back here, obviously this would just be the positive side, but there would also be a negative side here of that sine wave. We do full wave rectification, and we do 3-phase rectification. Full wave rectification reduces any order of harmonics that are divisible by 2, the even numbers. And because we do 3-phase rectification, we cancel out anything that's divisible by 3. So what we're left with is I believe it's the prime integers, or the integers, the 5th, the 7th, the 11th, the 13th. And what do those numbers mean? It means, all right, there we go. This is our fundamental frequency, 60 hertz in the US, right? So that's an ideal waveform. I'll get back to that in a second. once we start into rectification, we get those disturbances. Now, there are other disturbances in the system, voltage dips, power interruptions, commutations, voltage fluctuations, frequency fluctuations, over voltages, brownouts, blah, blah, blah. Those are completely uncontrollable for the most part. But harmonics, the important part of harmonic distortions is they are repetitive and they are continuous. So if I have something that's repetitive and continuous, I can anticipate it, I can plan for it, and I can correct for it. I'm sure there's different ways to correct for some of these voltage dips and rises and all that stuff, but if you don't know when it's coming, it's that much harder to plan for and that much harder to correct. If you know it's a repetitive continuous system, then it's a correctable event. As we talk here, harmonics refers to a component of the periodic signal. The fundamental frequency we said is 60 hertz. Sorry, Danfoss is an international company. In Europe, they do 50 hertz, so that's where that comes from. So 60 hertz here in the US, a second harmonic would be 120 hertz. The third harmonic would be the 180 hertz, and so on and so forth. So because we said we do full wave rectification, we get rid of the evens, and because we do three phase, we get rid of anything divisible by 3, we're left with the fifth harmonic, the seventh harmonic, the 11th harmonic, and blah, blah, blah. So what does that mean? Is I were to put a scope on that input line, I would see, if I could separate it out, I would see a 60 hertz line, but I would also see the fifth harmonic, which is a 300 hertz line. I would also see the seventh harmonic, which is a 420 hertz line. So overlaid onto this 60 hertz line, I've got a 300 hertz line, a 420 hertz line. The 11th would be a 660 hertz line. So as all those waves pile onto each other, you get that constructive and destructive interference, and you end up with this guy, right? Each one of those frequencies has a current portion associated with it. So that's where the problem comes in. For the most part, we've not really seen catastrophic failures as a cause of harmonics. You can overheat transformers, and okay, if you overheat a transformer to a given degree, yep, you could blow it up, you could catch it on fire, whatever, that would be a catastrophic failure. But we haven't seen anything that's been so horrific that this has been such a devastating problem. However, there are concerns in the plant. Again, we talked about causes, ballast lighting, DC switching power supplies, AFDs in the European world, adjustable frequency drives, variable frequency drives, frequency converters, drives, arc welders, things of that nature. Every one of these devices will cause harmonics in the system. Again, ballast fluorescent lighting, and these are examples of what some of those harmonic distortions will look like. And this one in the bottom left would be the VFD. Here's again where we talked about the rectifier, and this is the 6 pulses where we get the 6 pulse phraseology or whatever, the identifier of a 6 pulse drive. Pulsating current is drawn from the supply grid. Current pulse shape is dependent on the capacitor size. So that's one of the things that could differentiate drive manufacturers based on how they size their DC bus capacitors. And the current pulse shape is also load dependent, meaning as the load changes, increases and decreases, your harmonics will increase and decrease as well. So as we generate current distortion, which is what we see when we add those values together, we add the current from the 300 hertz line and the 420 hertz line, the 5th order, the 7th order, and things like that, we get a current distortion. That current distortion is seen between the drive and its supply. It's basically a path level. That current distortion, when it hits the transformer's impedance, it generates a voltage distortion. And the voltage distortion is what becomes system level. And that's kind of the key indicator here. If you look at the effects of current distortion, since operation of nonlinear loads causes distorted current, which is path dependent, the effect of current distortion on loads within a facility is minimal. I have a laundry list of what those effects are. We'll go over in a minute. Therefore, harmonic currents can't flow into equipment other than the nonlinear loads that are caused by them. However, the effect of current distortion on distribution systems can be serious, primarily because of the increased current flowing in the system. And here's a little list of what current distortion can do. Transformer overloads, tripping of serial relays, circuit breakers, stressing power factor correction. The big one here is premature aging of serially installed equipment, overheating of cables and insulation stress, overheating of transformers and insulation stress. So if you do nothing and you have high current distortion, by definition of what creates voltage distortion, the higher the current distortion, the higher your voltage distortion, which we'll get into in a second. But if you have high current distortion, you can start to overheat your transformers and stress your cables and whatnot. And again, I don't have any kind of documented how high can you overheat a transformer before it fails, but there are losses and there are inefficiencies. And when we think back about energy savings, we're seriously not getting any energy savings if we have losses in the system. So how does that affect voltage distortion? So it's the current distortion that actually generates the voltage distortion. So besides overheating, the other major effect of current distortion on the electrical system is the creation of voltage distortion. This distortion will have a minimal effect on the distribution system, but unlike current distortion, it isn't path dependent. So harmonic voltages generated in one part of a facility will appear on common buses within the facility. So if you think about the current distortion is going to be between the drive and the transformer and the cables right there. Voltage distortion is going to be between the drive and anything else that's connected to that bus, or potentially anything else that's within that facility. High voltage distortion at the terminals of a nonlinear load doesn't mean high distortion will be present throughout the load. In fact, the voltage distortion becomes lower the closer a bus is located to the transformer, which if you think about impedance, there's some cable impedance in there. So if you have shorter distances from the transformer to the drive, you'll have slightly lower current distortion, which would give you slightly lower voltage distortion. However, if excessive voltage distortion does exist at the transformer, it can pass through the unit and appear in facilities distant from the origin. So this goes back to a little bit of years ago when IEEE and the power utilities finally got together and said, you guys are using drives, you're doing weird stuff to our grids, we need to come together and have some at least recommendations on this stuff. And here's a description of our voltage distortion issues. Malfunction of electronic equipment, breakdown of electronic equipment, increased EMI, increased losses in direct online motors, which I'll go over to in a second, torque ripples from direct online motors, and erratic operation. So this is if anybody out there has experience as an electronics technician or an electrical technician, this is the one that you'll go chase the electrons through the plant, trying to figure out what's causing the problems. So this can be a much bigger issue. So here's an example. In the upper right-hand corner, that's our voltage distortion as a function of our impedance times our current distortion. Harmonics generally lead to poor utilization of the supply infrastructure, and you can read poor utilization as losses and inefficiencies. When we talk about energy savings, we look for things to be efficient, right? Reduced equipment life, lower equipment efficiencies, increased likelihood of trips and production stops. The thermal image on the left are two motors, both direct online or across the line without a drive. The upper motor is a thermal image of a voltage distortion less than, say, 4%. The lower image, I don't know if you can see that. Yeah, you can see that. Okay. The lower image is a motor with 8% voltage distortion in the system. The problem with that is from IEEE documentation, that motor will end up being derated to 85%. So you can obviously see the excessive heat in the bearings, some of the windings. The bearings get excessively hot, they'll start to vaporize some of the oil in the bearings. And guess what? When the oil goes away, the bearings get even hotter, and eventually the bearings will fail. So there's a classic example of what voltage distortion can do to a system. So what's a safe level? IEEE came out, I think there was one in 1980 something. I think that was the original one, 82 maybe. Then they did it again in 92, and they just released it in 2014. And it gives you some guidelines for voltage distortion, and it's based on 3 different levels. One is what was the first one? A commercial level, if you're thinking about office buildings, shopping malls, banks, hospitals, and that has a 5% max voltage distortion level. There's an industrial level, which would be identified for industrial plants, in my world, wastewater treatment plants, that allows voltage distortion to be up to approximately 8%. And then there is a third level, which is, I can't remember how they label it. I think there's an IEEE guy in the audience, but it's like a self-imposed thing, which you can go as high as you want because your own transformers are inside your utility and you can do whatever it is you want to do. So in the bullets on the right, you can be assured that there's already harmonics in your system. Unless you are a pure linear load system, there's harmonics there already. Current distortion is less important, but we want to restrict the voltage distortion. Product immunity has to be higher than system distortion to prevent breakdown, but product life is a function of the distortion level. And what we say is a good practice is aiming at the voltage distortion to be between 5 and 8%, and you'll avoid damage to your components. So here's our rule of thumb. Keep your voltage distortion at 8% or below. Look at the drive load on the transformer. If the drives on that transformer are less than 30% of the total load, you're probably going to be pretty okay. I know that's not a very technical term of pretty okay, but harmonics are probably not going to be an issue. If the transformer is loaded greater than 90%, you certainly want to do a harmonics analysis and get an idea what I might have to deal with in terms of mitigation. Additionally, if you have a generator fed supply or even a backup generator, in the water wastewater market, we deal with a lot of pump stations and a lot of municipal water treatment plants that say, hey, if the electric grid goes out, I can't stop pumping, so I have generators to back me up. And if that generator comes online and I've got 5 drives there, or 3 drives, or whatever it happens to be, drives and generators, they will play nicely together if they're designed to work that way. And if they're not, you can typically or commonly have drives that cause generators to trip offline. If problems occur, consider using special drives, using filters, change the layout, and mix single and 3-phase nonlinear loads. We'll go into some mitigation technologies as we go along. And this is an example. We offer a free harmonics analysis program. You input the transformer data, you input the drive data, and it will tell you where you are. This is a quick example. This was 4 250 horsepower drives with passive harmonic filters on them. And you can see at full load that was 80% loading, which is kind of industry standard for loading of a transformer at full speed. And our harmonic voltage distortion is 1% in the lower right-hand corner. And that results in a 3.2% harmonic current distortion. So we can do this really quick. If you have any questions on that. So any questions on the theory or the physics behind harmonics at this point before we start talking about solutions? Okay, so let's talk about mitigation techniques. As we went back here, we said, if you got less than a 30% drive load, you might not need anything. But as you start to look at your system and see what you can do, there are several different options. One I like to call a non-VFD mitigation technique. Then I have a passive technique, and then I have some active techniques. The non-drive mitigation techniques would be oversizing your transformers, put bigger stuff in. It could be balancing the load. So you have some VFD driven motors and you have some motors that are direct across line, because across the line motors will balance out some of the harmonic issues. So you can do some of that stuff. Is it easy? Maybe, maybe not. Nobody wants to oversize transformers. Certainly nobody wants to oversize generators. I'll just give you this bullet. If you want to ensure that your generator will play nicely with all your drives, have the generator 3 times the size of the drive load with no filters. Now that's not necessarily anything anybody wants to consider, because now you're paying, potentially 3 times what you would for a generator system. You can put some harmonic filters in there that will take care of that as well. So we talked about balanced distortions, no added hardware, but it could be impractical moving loads and moving wiring. Oversize, it's simple, it's not necessarily efficient. Use specific transformers. It's okay, but there are better solutions out there, or there are other solutions if you don't want to go that way. Drive-based passive harmonic solutions. You can use a DC link reactor, a DC coil. The alternative to a DC coil would be an AC line reactor. In the Danfoss world, all of our drives include a DC link reactor. And I have to give that a caveat because I know there's some non-water wastewater people here. In the Aqua drive, which is the water system drive, that includes the DC link coil. That's the FC202 series. In the automation drive, that's the FC302 series, that includes the DC links. If there are customers in the audience who are using the Danfoss micro drive, which is the low cost, I think it stops at 30 horsepower, that has no DC links. It's not designed for that. It's designed for the shaft turner applications and things like that. But anyway, you can use a DC link reactor, which Danfoss has. Many other drive manufacturers are using DC link reactors as well. It's built into the drive itself, and it will reduce the current distortion down to about 40%, which is fairly decent. And then you can look at what your voltage distortion is, and in many cases, you won't need any extra filtration systems. You could use a harmonic trap. We also call it a passive harmonic filter. You could do it as a single, or you could do it as a system-wide, where you can get harmonic current distortion down to about 5 or 10%. Those are very simple systems. We'll go into each one of these in a little bit more detail. And you could also use a multipulse. And years ago, multipulse solutions were very, very prominent. And when we get to those pages, I'll go over some of that stuff. Here's the AC input line reactor. And in the lower portion down here, this is our DC link reactor. So I'm just going to throw out some names that I know do this. I know Rockwell does this a lot. I think the Eaton guys do this a lot. But more and more people, and I know in the Rockwell PowerFlex 750 series, I believe, the latest ones have an option for a DC link reactor. The Danfoss drives do DC link reactors. I believe ABB does DC link reactors as well. Call them DC chokes, DC coils. DC inductors are typically built in for us. Overlapping magnetic fields in the inductor reduces the distortion. Offers moderate mitigation performance. What I'll tell you is that a drive with a DC link reactor built into it will get you about 45% harmonic distortion. A drive with an AC line reactor will get you about the same 45% harmonic distortion. The major difference between these two is the AC input line reactor needs a place to live and it generates heat. So if it needs a place to live, it means it's got to go into an enclosure somewhere typically, and it generates heat. And if it's in the enclosure, now you've got to compensate for some of the heat losses. DC link reactor's internal. Does not generate the heat, does not need a place to live because it's already built into the drive. Here's the electrical physics difference, if you will. And what the takeaway on this chart says, as AC impedance increases on the AC side of the line. Yeah, what does that mean? As the AC impedance happens before the drive, meaning the external AC input line reactor, my DC bus voltage becomes less stable. That's the chart on the left with the squiggly lines here. But as DC impedance increases on the DC side of the drive, meaning after rectification, before the DC bus voltage, the DC bus section, my DC bus voltage actually becomes more stable. So what does that mean? It means your capacitors are a little bit happier, so to speak. As we talked about that 6-pulse ripple that comes off the rectifier, it's a 6-pulse signal. When you run it through a DC link reactor, it knocks that ripple down and you get a smoother flow to the capacitors. Capacitors like smooth input and output flows as opposed to pulsating inputs. Again, here's our 6-pulse rectifier. I mentioned at the beginning of the presentation, there's a little bit of repetition here so that we see it in different forms. As we rectify, we cut off the tops. Remember when the voltage rises up here, so it's above the DC bus voltage, current will flow. I get 1, 2, 3, 4, 5.5 here, and the other half here for 6 pulses. That's where the 6-pulse comes from. And this would be another graphical depiction of a 6-pulse versus a 6-pulse DC link and an AC link, and then a 6-pulse with no chokes at all. So the harmonic current in a 6-pulse drive with no chokes, your fundamental current at your 60 hertz is 38.5 amps, roughly 40 amps. But because of the harmonics associated with this curve, it looks like I'm using 55 amps. So 40 amps is actually being used to generate torque in the motor. But the transformer is seeing 55 amps. Guess what the power utility is billing on? They're happy to pay that, or they're happy to charge that, right? If you put an AC input line reactor over on the right side, your fundamental current is 36 amps. You're generating 43% harmonics, and it looks like you're using 40 amps. So you're using the power better, right? And you've got less losses. If you use the Danfoss solution in the middle, that's our DC link reactor, you're using 36.2 amps, generating 42.5% harmonic distortion, and it looks like you're using 39.7. So again, between these two, from a harmonic standpoint, it's pretty much a push, right? 39.5 versus 40, it's pretty much the same harmonic performance. The benefit is mine is built into the drive, so it doesn't need a place to live. AC link reactors are typically classified in a percentage, a 3% line reactor or a 5% line reactor. What that means is they're going to eat up 3% of the voltage supplied to the drive, or 5% of the voltage supplied to the drive. So if you're reducing your input voltage to the drive to a certain degree. So there are benefits here and there for that. This is the multi-pulse system. And I'll give you the background, and if there's anybody in the audience that has more detail, I'm more than willing and happy to listen. It was about 25 years ago when harmonics were there, because drives were there, because we always said drives create harmonics. Drives started to become more popular. The problem is harmonic issues started to arise, and people started to say, how do we fix this? A company called Robicon, and I could be wrong, but I'm pretty positive it's right. A company called Robicon came out with an 18-pulse solution and said, we fixed the harmonics issues. And what they did is they basically took 3 sets of rectifiers and put them in the front end. And they took those camel hump curves, if you will, and they phase shifted them 20% up, neutral, and 20% down, and used the overlapping theory and came out with this sine wave. And as you see here, we're using 36 amps, we're generating 8.9% distortion, but it looks like we're using 36.2 amps. So we're actually using the power really, really well. The losses are significantly less. And 25 years ago, it was really the only solution on the market. So everybody said, this is great. We're going to use 18-pulse and multi-pulse drives everywhere. A couple of downsides. Number one, this little gizmo right here is known as a phase shifting transformer. So I take 3 wires in, line 1, line 2, line 3, and I take 9 wires out. This is a rectifier bridge, this is a rectifier bridge, and this is a rectifier bridge. Phase shifting transformer is not exactly miniature. It's fairly large, generates heat, needs to sit in a bigger cabinet. And it's based on the fact that the 3 wires coming in are equally balanced. Minimal voltage distortion, minimal phase imbalance. When I say minimal, less than 1 to 2%. You get 2 to 3% voltage distortion or phase imbalance on the inputs, this chart goes off, this curve goes off the charts. I'll show you what that looks like in a minute. Again, here's another example. 12 pulses there, and 18 pulses. 12 pulse just uses 2 rectifiers, 18 pulse uses 3 rectifiers. There are drives on the market that are known as 24 pulse drives. You can imagine what that is. You just got that many more rectifiers in the front end. That's fairly common in medium voltage applications, but these are low voltage applications. The well-known technology, power coming to the rectifier sections is phase shifted by special transformers. It offers fair mitigation performance dependent on high load and grid stability, and that's the biggest issue. I would challenge you to go out to your power utilities and don't ask them, but read what's coming off your transformers. Motors were typically designed at 460 volts. They boosted that up to 480 volts. I've talked to guys that are installing drives, and I said, what was the input power to your drives? And I said, 502 volts. Yikes. So they're not necessarily the most stable grid. Optimal for step down, step up solutions. They're robust. There's no moving parts, right? It's just a phase shifting transformer. And back then it was fine. And here's the examples. I've enlarged the ones on the left because this is the 18 pulse solution. The one on the right is the 12 pulse solution. But the larger dashed line is 18 pulse with ideal balanced power. And that's right down here below the 10% line. And that's actually pretty good if that's what your power is. If you get 2% voltage distortion, you end up with this dashed line, which you're never really into harmonic compliance until you're about the 80% range, somewhere in here. Right? The solid lines are passive harmonic filters, and the solid red line is an active harmonic filter, which we'll get into in a few minutes. Come down here in the bottom left corner, you're talking about phase imbalance. 1% phase imbalance across your line 1, line 2, and line 3, your 3 phases, puts you on this line, which isn't bad, but again, you're 50% until you get some harmonics compliance. If you get 3% phase imbalance, you're almost never in compliance. So the interesting thing I've found here, I've been with Danfoss for 10 years. The interesting thing that I've seen in the proliferation of 18 pulse drives, there are so many engineering, consulting engineers that will simply specify it's over 100 horsepower, it's got to be 18 pulse. And there are many, many customers that have them out there, but they all have harmonics, they just don't see it. So you have to ask the question, is power really that perfect? Which I would challenge to say it's probably not. Or are the harmonics that they're seeing not that detrimental to their system? The benefit for us as salespeople is that all of those Robicon drives from 20 years ago and less are now 15 to 20 years old, and they're all approaching their end of life cycle, and they're all large. And if you have any of those out there, we can easily leave the panel in place, take the drive out, take the phase shifting transformer out. There's boatloads of room in those panels. Put a Danfoss drive, or if you elect someone else's drive, and a passive harmonic filter, and there's still plenty of room left over. So you can retrofit those panels very easily. And that leads me into the passive harmonic solution. When I get into passive harmonic filters, I simply compare this to the orange foam earplugs that are typically on the wall before you go into the machine room or the pump room or wherever. You roll them up, stick them in your ears, and they're decibel level filters that are designed to allow a certain decibel sound level to pass through, so you can still hear people talk, but it filters out some of the higher decibels. Right? In a passive harmonic filter, we have 3 wires in, 3 wires out. We have a reactive portion, and we have a capacitive portion. And in that filter, it's designed as what's known as a low pass filter. So what does it mean as a low pass filter? It means signals below a certain level are allowed to pass. When we say pass, they go from the transformer supply to the drive. They'll pass back and forth. Well, if we know the 5th harmonic is a 300 hertz signal, and the fundamental signal is 60 hertz, we would say that anything at 60 hertz and below is allowed to pass back and forth. Anything over that, like your 300 hertz line, is going to get trapped in this capacitive circuit. And that's how your passive harmonic filter works. Several manufacturers, quite upfront, I use MTE matrix filters. There's Transcoil TCI is one that I know of. I actually make my own. The company probably wouldn't be happy with me saying this, but I make my own. I make them in Germany, and they're typically longer lead times. And I do not include a capacitor disconnect in mine. The MTE matrix filter does include the capacitor disconnect here. So that's a big benefit. When you reduce speeds and loads on the drive, you can take that capacitive portion out of the system. And then if you're running on a generator, you don't have any power factor issues, leading power factor issues there. So off-the-shelf design, retrofittable. Typically, they're in two options, a 5% current distortion or 10% current distortion. Personally, that's my preferred system. And it's so much that it's my preferred system that we actually developed or packaged, we didn't really develop it, but we packaged an offering we call a PHD, which is a passive harmonic drive or a preferred harmonic drive. And here's what it looks like. Here's the drive in the upper left corner. This happens to have a soft start bypass in the middle of it. And then here's my MTE matrix filter. This is the filter. There's the capacitor contactor, and there's the capacitor portion of that filter right there. This is a really, really nice, elegant solution. 3 wires in, 3 wires out, NEMA 1, NEMA 12, NEMA 3R, up to, I want to say 650 horsepower. IEEE 519 compliant. This product actually comes with a performance guarantee. So from a IEEE standpoint. So it's a pretty sweet system. And here's the performance. So my red dashed line is my Harmonics Performance. My blue dashed line is what we call an active front end, aka Regen, which I'll get into in a few minutes. And then the green line is your 18 pulse. So it's based on load speed. And then here's power factor on the right-hand side. So PHD, the passive system will maintain power factors a little bit better as speed reduces compared to the other guys. So if a passive harmonic filter is equivalent, in an analogy, I guess, to the orange foam noise canceling earplugs, the active harmonic filter is equivalent to a noise canceling headphone. Active harmonic filter connects to the power inputs to the drive. It reads with current transformers what the existing harmonics levels are, and it injects currents in counter phase to give me as close to a perfect sine wave as possible. Induces anti-harmonics, that's not really a word. Size to allow some distortion, but it's an engineered solution. We have pre-configured drive packages. It can be a system solution or it can be a single drive solution. The benefit here is if the filter fails, the drive still operates. That can be said as well for the passive harmonic filter. If something happens to that passive filter, your drive still works. So, things to think about. And I can show you something pretty interesting, maybe. This is a 450 horsepower drive in a lab in Rockford, Illinois. It's pulling about 430 amps. It has an active filter connected to it, but it's turned off. And as I hit play, you'll see that that's not a sine wave at all. Pretty ugly. But in about 3 or 4 seconds, I'm going to turn the active filter on, and you'll see the current go down and the sine wave clean up. So that's the results of what looks like the incoming scope from an active harmonic filter. We went from 430 amps to 410 amps, so there's an energy savings, and we clearly cleaned up the sine wave. Offers high performance mitigation, Filter cancels the distortion by sensing and inserting an equal signal with the opposite phase. Tolerant with load and grid imbalances. It is more expensive than a passive solution, no question about it. You can do it from a system level. You can do it from an individual level. I make them. ABB makes them. I want to say Schneider makes them as well. Many of the drive manufacturers make their own. In my world, I can offer you a standalone active filter, or starting at 250 horsepower and above, I can bolt that active filter right to the drive itself and supply it as a system. We call that a low harmonic drive. And again, there's another example of what we look like. So we have our distorted waveform from Harmonics. We have a signal that we're injecting back into the system to create the nice clean sine waveform. And there's my noise canceling headphones. Parallel installed device measures the distortion, compensates for unwanted current, actively imposing signals in counterphase to the unwanted current signals. These are excellent solutions if you have several drives and you want to spread one active filter across several drives. I did a job in New Jersey that was 8 100 horsepower NEMA 4X outdoor mounted drives, mounted over the aeration basins, connected right to the surface mixers. They didn't have any room to mount the drives in a building. NEMA 4X, you don't have to mount it in a building and mount it right outside. But they said, well, there's 16 of them total. That's roughly 1,600 amps of current that's going to be used, roughly 800 amps of harmonic current that will be generated to cross the street from a cogen facility. It's a very high densely populated area of New Jersey. And so we better do something for harmonic filtration. So the bank of 8 drives were fed by one panel, one MCC panel. We said if you put a 400 amp active filter at that MCC panel, it will mitigate all the harmonics from those 8 drives on that system. And we did that in 2 different sets. So we have a 400 amp filter, 8 100 horsepower drives, no problems with harmonics at all. And then we have another duplicate set on another system. So it works well. When you start to look at, and I think I said this in the beginning, there is no one size fits all when it comes to harmonics mitigation. You need to look at the system. You need to look at the space available, the real estate. In some cases, you need to look at temperature. Is it going to be in a hot environment, or is it going to be in an air-conditioned controlled room, things like that. And you can start to apply different products accordingly. Along the lines of the active filter is what I call the regen drive. So several years ago, a few drive manufacturers came out with applications, and again, I believe there's some industrial guys in the room, where you have situations where the load becomes generative. In other words, the motor starts spinning faster than the drive wants it to go. And that motor just became a generator. Well, as that motor is now a generator, it has to send that energy somewhere, and the only place it can send the energy is back to the drive. One option is a brake resistor, which is fine. You just blow off that extra energy and heat, and it's wasted. But another option, which is kind of cool, is you can take that energy from that regenerative load and put it back on the grid, which is kind of cool as well, because now you're regenerating electricity. Engine test stands, generator test stands, lifting systems, cranes, hoists, DC to DC grid conversion systems. Those are great. Shaft generator systems and shipping, those are perfect. Remember, I'm a water wastewater guy. And I tell people, if my raw sewage pump just started spinning faster than the motor wants it to go, I've probably got bigger problems in the plant somewhere. So from a water standpoint, I don't recommend a regenerative drive. There are some issues, not necessarily issues, but there are some things to consider with it. The difference between a regenerative drive and a standard 6-pulse drive is a regenerative drive does not use diodes. The diodes are uncontrollable, right? It's just a little switch, and when the voltage gets high enough, the switch opens like a check valve in a water flow. The regenerative drive uses IGBTs on the front end as well as the back end, and it's a controlled pulsing. It controls when those IGBTs open and close, so it has some control over the waveform that's coming to the drive and going back to the transformer. There are a couple things to consider. It boosts DC bus voltage, because remember in the beginning when we said that diode only opens when the voltage in that phase is higher than the DC circuit. In order for the energy to go back out onto the grid, the energy in the DC bus circuit has to be higher than the incoming energy. So I've got to have this up fairly high. And that can have some effect on output DVDTs and voltage spikes to the motor. Some, not all, but some. If the IGBTs fail, you lose the whole drive. There is another thing to consider from a harmonic standpoint. IEEE typically goes up to the 50th order harmonic. And let's see, 6 times 5 is at 3,000 hertz. When you get into high frequency harmonics, and this is high frequency switching, it doesn't address that. And there are some issues with high frequency noise in systems that can have some problems. So things to think about. If your process or your load becomes regenerative, again, lifts, cranes, hoists, test stands, that sort of thing, it's a great solution. Danfoss offers them. We offer them in the Vacan products. It's an excellent solution for that. But if you're looking at water, wastewater pumping, it's really not necessarily needed. And you have higher losses. The diode rectifier will have much lower heat losses than an IGBT system. This guy's generating more heat than a basic rectifier system. So here's some examples, and again, this engineer in Texas wanted to see the difference between a 6-pulse passive filter and a regen drive. And then we did it again with an 18-pulse drive. And the data here comes from an MTE white paper, and I have a couple other slides that actually reference the author. This is a 6-pulse drive with a passive harmonic filter, and then you can see the regen drive is the dashed line when you look at Harmonics Performance. And again, here's the matrix filter functionality. They wanted to know a little bit more about how it worked, what it did. It has some circuits here that filter out or tune to the 5th order harmonic. And we talk about losses. Passive harmonic filter losses drive horsepower. And this makes sense, remember, because we said in a regen drive, you have those IGBTs on the front end, which are going to generate more heat. More heat's more losses compared to a passive system. So your losses could be fairly large, and losses can come down to efficiencies. Right, so again, here, your passive system is approximately 98% efficient across the board, but your regen drive is going to be less efficient because you're generating those that heat energy in the front end as well as the back end. And then this is an example of total harmonics, right? So the solid green line is 2% imbalance with a passive system. The maroon line, if you will, is 3% imbalance. The dashed green line is 2% imbalance with a regen drive, and the dashed red line is 3% imbalance with a regen drive. So, and there's the author of the MTE white paper. If anybody wants a copy, just let L3 guys know. I'll make sure you get one. I think they have one already, by the way, but questions?
Joe, we actually had a question when you were talking about the transformers being over 90% loaded with the harmonics. The question came from Donald Ray.
In this one or back here?
Back there, yeah. And it said, should you take the extended capacity 55/65 degrees C rise and fan cooled of a transformer into consideration when looking at the percent loads?
I would not. I would run it through the analysis and see what filtration systems I need to add, or what mitigation systems I could add that gets a transformer loading down to about 80%. That's going to just guarantee the best performance.
Okay. Well, you know, 50.6 degree means that's 2 ratings. So you got like extra 15% capacity if we go to the 65-degree rating. Obviously, there's more heat generated in the transformer, which there's more losses. So
Right.
trying to save energy, then
Yep. I would err on the side of safety in that case and use the lower rating. It doesn't take a whole lot of mitigation systems to bring things into line. And again, it would look at, you know, if you're higher loaded, but your voltage distortion is still in that 5%, 8% range, I think you'd be fine.
Don, did that answer the question? Y'all can unmute yourselves if you want, or I can try and unmute everybody. I don't know what will happen.
John, this is Rich Carlstein. I've got a question.
Go ahead.
There was this harmonic analysis. Is this some software?
Yep.
I guess.
Yep.
And what about is it based on having newer equipment, or if there was just simply the data off of your equipment? In other words, if I got a lot older gear, can we still do this?
Yes, you can. I'll show you an example of what it would look like. I did this for a customer in El Paso. All we really need is the transformer data. I can show you some different things. This is what our report comes out at. And the design engineer made the assumption that El Paso Electric will provide a 1,000 kVA transformer, 5.75% impedance. So we put that data in. The system will pick, actually I redid this at 750 kVA. The system will pick a generic impedance or a typical impedance of that transformer. And if it's actually different, in this case it was different, it was about 5.6, I believe. And the engineer asked me to rerun it, and it didn't make a difference. He actually also asked me to do the short circuit power. He said 99.99 is a little unrealistic. And I said, it's unrealistic, but it assumes the absolute worst case scenario. So we changed the impedance. The short circuit power came down to 167. And you can see here we've got 3 250 horsepower drives at 100% speed with a 5% harmonic filter. And there's what our result came out to. 1% voltage distortion, 3% current distortion. So it doesn't really care how old your system is. When we talk about installing drives in aged applications, like an old motor, then I look at what's the condition of the motor. And I look at, you know, has anybody measured the motor lately? Has it been rewound lately? Has it been on a drive and you're retrofitting from an old drive to a new drive? Those kind of questions come up. But when it comes to transformer stuff, we simply look at transformer data. I can give you a really quick example of how simple this is. This is off the Danfoss Drives website. Look for the software download section. You simply input the transformer data. Let's say it's a 750 kVA. It'll come up with an impedance. If you know something's different, you can input that yourself. 480 volt, 60 hertz. What drives do I have? I'm going to add FC202 aqua drives. I'm going to make them 200 or 250 horsepower. Let's say there's 4 of them. At full load, I've got no harmonic mitigation. So here's harmonic filtering right here. I've got none. And here's the result. 8% voltage distortion, 23% current distortion. Your transformer's loaded at 116%. So somewhere you go, it's probably a good idea. Even though your voltage distortion is at 8.3, you're not IEEE compliant, do you really have to be? Well, in this case, at 112% transformer loaded, I'd say we need to do something. You come back up to the frequency converter data, edit it, add a passive harmonic filter. Okay. Back to result. Voltage distortion 1.2, current distortion 3. I'd still be concerned about 109% transformer loading. That would be something you might want to consider and look at your overall system. You could go back and say, all right, what if it's a 1000 kVA transformer? Everything else remains the same. Now my transformer loading is at 80%. Voltage distortion is at 1.1. Current distortion is 3.2. I'm good to go. And that's a free downloadable system. You can customize this thing with other things. You can add non-Danfoss frequency converters. You can add other motor loads. If you know there's a couple 100 horsepower, 50 horsepower, whatever the total motor load is, it's direct online. You can add power faction correction. You can add cable lengths. You can play with all this. Leaving these zeros is worst case scenario. So you can go in there and add cable length if you know what it is, but it's not going to have a massive effect on your result.
That looks like a really good tool. So I'm going to definitely give some of this stuff a try.
Oh, it's great. I love it. I mean, you can do just how long that took to do. You can run that through while we're talking and say, hey, you're going to be fine with this. And here's, if you really want to look at some fun things, if we go back to the drives and we say there's no harmonic filters on the drives. So what I say, there's 4 of them, right? So there's 4 drives here, 25% current distortion, 85% loaded, because we're on a 1000 kVA transformer now, with 7% voltage distortion. So I'm not really harmonically compliant. Would I be worried at 7.2%, 85% loading? This would depend on the process. Am I a remote lift station with nothing around me? Probably be okay, maybe. In the municipal water world, we live in the world of redundancy. So the odds that they're running all 4 of those at the same time at full load is absolute worst case scenario. Most likely they'll run 3 drives and the 4th drive will just be a spare, or they'll cycle it through in a alternation. But if I wanted to see what happens with an active filter, I could add a standalone active harmonic filter. Let's say I do one at 310 amps. The active filter has a choice between doing harmonics or power factor correction. I'm just going to do overall compensation of harmonics. And I look at my result here, and boom. 83% loaded, 1.9% voltage distortion, 4.7% current distortion. So a single active filter can mitigate all 4 of those drives on that transformer, and you'd be fine. So it gives you some flexibility in how you want to do things. Any other questions?
Yeah, we got 3 other questions that popped up. Do you see the pop-up of the questions?
Hang on. I will when I get right back to the right screen.
Oh no, you got 4, I only got 3. We answered Donald's question, okay. All right.
Cool. If there's no other questions, thanks for your time. Enjoy your holiday weekend and be safe.
That was great.
Thanks again, Joe.
Thanks, Joe.
Thanks, guys.